Welcome to the 12th lecture for Physics 4B. In this lecture, we introduce the electric potential, which we will most frequently refer to by the name voltage in this class. We start by introducing a commonly used, illustrative physical setup for discussing ideas in electrostatics. Two oppositely charged, infinite parallel plates. With this setup, we go through the mechanical considerations of a test charge, arriving at the ideas about voltage in ways very similar to how we arrived at the electric field. We do ultimately define voltage difference in terms of electric field. Just as we had the graphical tool of electric field lines with electric fields, we have a similar graphical tool in helping us visualize voltage distributions using equipotentials. When drawn on a two-dimensional screen, we talk about equipotential lines. In the actual three dimensions, we have equipotential surfaces. And we introduce what I call universal reference point, referring to a common assumption made in deriving most of the commonly derived and memorized voltage formulas. By the way, if you remember the derivation of gravitational potential energy using Newton's law of universal gravitation in Physics 4a, what you see here now should be a familiar reminder of something that you already knew. That's it for this lecture. In the next lecture, we will talk about two additional conductor properties and capacitors. And we are almost ready to wrap up electrostatics. So let me draw this picture that we are going to use to motivate the next thing that we are going to talk about. How many here have heard the word voltage before? Almost all of you. Do you know how voltage is defined? Yeah, so that's what we're going to do. So this is the physical setup that I want you to think about. Well, maybe I shouldn't draw it. This is the physical setup that I want you to think about. So I guess I should explain some parts of it first, because it's an application of some of the things that you should know. So this is supposed to be an infinite plane. Good? You know what the electric field, well, I mean, this part is not infinite, but you know, this part, say, you can approximate as being infinite. You know what the electric field from these positive charges will look like, right? That's what the field lines are here pointing to the right. Now, if you didn't have this other plane over here, what you would have is you would have electric field lines pointing to the left as well, right? Infinite plane, you have electric fields pointing away from it. Okay, so that's the positive plate. Let's think about the negative plate. So for this negatively charged plate here, so the electric field to the left of the plane, will that be an electric field that's pointing towards the plate? Right? Pointing, yeah. What about on the right-hand side? Will it be pointing to the right or the left? To the left, towards the plane, right? So this is what it should look like. Now, so here's the question. So in between planes, all right, it all makes sense. We don't have to change anything. So in this picture, why are there no, for the net electric field, why are there no electric field lines drawn here or here? Well, no, I don't think you meant it the way I would interpret it. No, I mean, do you guys remember superposition principle? Somebody state superposition principle for the class, please. What does the superposition principle say? Let me restate the question. So this, by the way, I should probably do this in two different colors. So let me redo the one for the negative charges with the blue color. So this is what the electric field due to this negative plane would look like. So so suppose I want you to find electric field at this point. I want you to find what is the electric field at this point.
So you might go to, so this positive plate, it's going to generate electric field according to that formula that we derived. So the electric field due to the positive plate would look like a sigma, whatever charge density it has, over 2 epsilon naught. And it'll be the same magnitude here and here, but just the different directions. Now, if I'm looking for the electric field here, can I just look at the positive plate and say, that's my electric field? Can I do that, or do I need to go further? Are these the only charges in the system, or are there other charges in the system? Yeah, there's the negative charges there. It's still there. It's farther away, but that's there. So you have two sources, positive plate and negative plate that can be generating electric field. This is where superposition principle comes in. What does the superposition principle say about how to find the electric field here? If you already know the electric field due to these two sources, they have the same electric field magnitude. So what does the superposition principle say about what the electric field here should be? No one here remembers the superposition principle? I guess we didn't spend a lot of time, but it's an important underlying principle. We actually mentioned it when we were talking about waves, wave interference. It's the same principle. You just add them. Yeah. So that is a sense in which they are not interacting. As in, if you just took these charges away, the electric field from this will just remain as it was there before. When you add these charges, now these charges might respond, but the electric field here, you simply add the contribution to the other charge. And that's because one electric field doesn't interact with another electric field. It interacts with a charge, but not with another electric field. So what's important for you to remember is that superposition principle applies to electric fields. So for the electric field here, we can simply state it as the electric field as a vector quantity due to the positive plate, plus the electric field as a vector quantity due to the negative plate. So let me ask you this. At this point here, the magnitude of contribution from the positive and negative plate, are they same or different? Yeah, they're the same. So it would be a different question. If I had, let me get out my equal sized balls. If I have 2-point charges, and if I asked you what is the electric field, contribution to electric field, if I have 2-point charges, and if I ask contribution to electric field at this point here, then you would say, well, this charge has greater contribution because it's closer. The thing that's special about the plane of charges is that, as you can see in this formula, it's independent of distance. To the extent that you can treat this plane as infinite, it doesn't matter how far away you are. So the contribution from the positive plate and the negative plate has the same magnitude. So it becomes a question of, if I extend these electric field lines, so the field lines pointing towards the negative plate, it comes out all the way over here. It doesn't stop at the positive plate. The contribution from negative plate, this field line due to the negative plate, comes all the way out here. It comes all the way out here. Yeah. So it becomes a question of, all right, at these different regions, how do they add? How do their magnitudes subtract? So on this side of positive plate, are they subtracting from each other or adding to each other? They're in opposite directions, right? So on this side of the plate, we can say that electric field is equal to 0 because they will just cancel each other out. What about in between? Are they pointing in the same direction or opposite direction? Look carefully, sorry, let me draw it. So this is the field line that would come from positive, same direction, right? Yes, same. So in between, the electric fields actually add. So the total electric field in between these two plates, it becomes sigma over epsilon naught. As though this could get any simpler. Well, it gets simpler. You get rid of the factor of 2. And what about, so let me continue this field lines here. If I continue this field line all the way over here, what about the region beyond the negative plate? How do those contributions add? Yeah, so they are in opposite directions again. So out here, the electric field is 0 again. So this is an arrangement that you are going to see a lot throughout this class. One of the reasons is that this is a very practical arrangement. If you want to build like an electrical apparatus, think this is a picture of a cathode ray tube. So this is how you do it, actually experimentally. And when you want to talk about capacitors, hopefully next Monday, if I get to everything I want to get to today, then this is the arrangement that we imagine for capacitors. So this particular arrangement of charges is something that you will see a lot throughout the semester. So I want you to spend a little bit of time to make sure that you understood the details of how it's set up. If you change this to 2 infinite lines or to point charges, everything here changes. What we are discussing right now, the exact cancellation outside, exact cancellation on that other side also, it only works for infinite planes. Yeah? All right, so that's the setup, but that's not what I really wanted to talk about. But do you feel like you understand the setup here? 2 infinite planes, one positively charged, one negatively charged. The nice thing about it is, so having 0 electric field outside is nice, but that's not the nicest thing about it. The nicest thing about this setup is that I have set up a constant electric field in between the plates. At least as long as you're not too near this field. As long as you're somewhere near the middle, you have this nice expression for the electric field. Now, let's say here's a question that one might ask, especially if you are building a cathode tube to fire cathode rays at something. Maybe you are building an X-ray machine or something. Yeah, X-ray machine. I don't think it's quite doomsday machine. Then one of the questions that you might want to answer is that imagine you have a positive charge here. Maybe it's a positron. And you want to figure out if the positive charge is accelerated all the way from one side to the other side. Let's say this plate is separated by some distance d. Then when this has reached the other side and it's exiting, what is its velocity? For example, that's a question that you might ask as you're designing the apparatus. How would you answer that? So this is almost like a physics 4a, right? Charge of charge q and mass m. There's some electric field applied to it, gets accelerated through distance d, and then exits through a tiny hole that's made there. And as it exits, what is the speed? That's the question. How would you answer that if you saw that in physics 4a final? Energy is 1. Yeah. How are you going to answer that?
Use Coulomb's law to find the force.
Now, you wouldn't use, what do you mean by Coulomb's law?
Force on the charge equals K times the difference in charges.
Force is equal to what?
K times the difference in charges.
Okay. I would not use Coulomb's law. Because here's what you have to remember. So this, so from this point on, when I say Coulomb's law, this is what I call Coulomb's law. The nickname for this is also Coulomb's law. What's special about this formula? Is it always applicable to every single situation dealing with the charges? No. What's the condition for you to be able to use this formula? That you're dealing with the point charge. So here, I'm explicitly not dealing with the point charge, especially in the sense that the charges that are applying force on, so this is point charge, but it's not interaction between 2 point charges. It's interaction between a distributed charges and a single charge. So, and besides, trying to use Coulomb's law here is redundant. That's really why I was emphasizing last time, or sometime, I think it was last Monday. It's really important that you understand the power of this expression. I say this like a dozen times in a semester, and people don't realize it because the expression I'm writing down is simple. But just because it looks simple, don't ignore it. This is the definition of electric field. That electric force is given by charge times electric field. Let me ask you this question. In this picture, do you have everything you need to calculate force? How would you calculate force? Yeah, Q times the electric field that you are given. Like if you just because this looks simple and you ignore it, you are setting yourself up to miss really easy questions. Because it's an easy question because I gave you the electric field. I did all the work for you. And I asked for something really simple like, what is the force on this charge? And the expected answer is, since you have electric field and charge, it was supposed to be charge times sigma over epsilon naught. But if you don't remember this definition, if you don't remember this, you will not see that really simple way of answering that really simple question. So I really cannot emphasize this enough. Like I do this, I go through this song and dance, but half of you will forget this on an exam and try to do a simple question in a really complicated way. So please don't underestimate this. This is your starting point. So we use the Coulomb's law to introduce the ideas in electrostatics, but I'm not going to go back to it. Coulomb's law it's elementary. It's the kind of electricity that you cover in middle school and high school. This is college. So the way we handle electricity is we have tools that will help us figure out electric fields under various different situations. Once you have electric field, then you use this to find the force. It's a two-step process. And the finding electric field, that can be complicated. That's why we introduce tools like Gauss's law, and we spend some time doing that. So here, so you have a charge, you can figure out a force. The question still, it goes down to the same thing. So I'm asking for the velocity here. Crystal suggested maybe we can use energy conservation. Does everyone here want to use energy conservation? All right. Okay, let's say I want to use energy conservation. Let me simplify this much. Let me say that at this point, I'm going to define my potential energy however I can, so that at this point, potential energy will be 0, right? And I can, I'm just trying to cut through some of the discussions that we might have to go through, but, cut through that. And at this point, let's say I can say kinetic energy, and I can write that down in an expression that involves the velocity. 1/2 mv squared. All right, so I can try to express the energy here. Now, here's the question. I have to know the expression for the energy here at the beginning point. So, like most of you do, I have an intuition that energy will be conserved in this situation. So I want to say initial energy is equal to the final energy. Final energy, I feel like I can handle it. I can write down an expression for potential and kinetic energy, and it'll be fine. But the question is, what is the expression for the initial energy? So I think I can say what the kinetic energy will be. Let's say it starts out at rest, so that I can say kinetic energy will be 0. All right, what's my potential energy? And where is that potential energy coming from? So in physics 4a, you always had the gravity, right? So whenever you're talking about potential energy, you are either talking about gravitational potential energy, or in some cases, you actually saw the spring in the problem. So you are talking about spring potential energy. So here, I want you to remember the more general relationship for potential energy. We didn't spend a lot of time on this in class, so you might have forgotten it. But if you go back through the chapters and read it, this is something that was covered in the textbook somewhere, that potential energy is always associated with a conservative force. So you have to identify a conservative force like gravity or spring force. And the potential energy is defined this way. It's change in the potential energy. So you are imagining going from some point A to B, right? And the change in the potential energy is given by the amount of work done by conservative force going from A to B. But actually, it's not equal to the amount of the work. It's negative of the amount of work. Or if you write out what the definition of work is, change in potential energy is equal to minus the conservative force applied as you are going from A to B times the change in the position as you go from A to B. Does this ring a bell? Yeah, your textbook does cover it. In fact, this is the description that I introduced, and I should have done it, when I derived the formula for the spring potential energy. Because we look at the spring amount of work that spring force does, and negative of that is the energy that's getting stored into spring potential energy. So I guess here are two questions that we need to ask. One is electric force a conservative force? If it is, what criterion are you using to say that this is conservative? Like, what's the criterion for something being a conservative force? I don't know if I say this in every physics 4A class. I think I try to say it. Sometimes I might not end up being able to say it.
There's no network done by the energy?
I mean, there's obviously work being done here. Otherwise, there wouldn't be change of potential energy. So it's a question of what allows you to say that the work done by the force wasn't wasted, but it was stored in some format. There has to be one particular feature there that you need to be able to say this force has, so that you can say it's because of this feature, we can say this force is conservative, yes.
It's not created or destroyed?
Create or destroy what?
Any of the things that you just said are conservative. But
Once again, you're not dealing with energy.
I think you just said, never mind.
Yeah. It has to be dealing with the energy. So I don't want you to get confused by the word conservative and get sidetracked by other conservation laws. We are strictly talking about energy. So here, let me give you an example of a non-conservative force, friction. When I push this block from left to right, you know that friction was at work, and you know that when we are talking about mechanical energy, friction force did something to it, right? Mechanical energy that used to be here at the beginning is no longer, here. It started out with some kinetic energy, that's gone, right? But so we say friction is not a conservative force. But somehow, we don't say that with gravity, even though gravity can be used to take kinetic energy out of a system. I throw this ball up, and if I catch it right at the top here, at this point, the kinetic energy is gone. But we don't say that that energy is just gone. Somehow, we come up with this idea for potential energy, where the kinetic energy that was gone was somehow still stored into another form of mechanical energy. So a given force has to have this particular property for you to be able to say this. So it's some general feature that's distinct between a friction force and gravitational force. They are both external forces in this case. Friction force is external to this block. The gravity is an external force to this ball. So yeah, that's not the distinction. I know when we are talking about conservation of momentum, that their internal external distinction mattered. We are talking about energy. Once again, there's many different conservation laws. We are talking only about energy. Yes?
One of them's a contact force, one's at a distance?
Doesn't matter. Spring force is a contact force, but it's a conservative force. Right? Spring force is a conservative force, but it's a contact force. So good guess, but that's not it. Yeah. So being able to say that the energy that was taken out by the work done by conservative force. So here you are essentially saying that it was deposited into a different form, that it's not wasted, right? So the way I like to describe it is it has to be predictable. The thing about friction is that it's not predictable. If a friction was a predictable conservative force, as I push it here, it would be a type of force that's directed to the left, and it would be constantly directed to the left. Now you might say, isn't that true? As kinetic friction is applying, you might say, oh, there's a mu k and force pointing to the left. But friction it's fickle, it's unpredictable. Because at the moment this block comes to a stop, friction force goes away. It's not there anymore. If it was a predictable force, then you would continue to point to left, and it would accelerate this block back to the left, giving the kinetic energy back. That is exactly what happens with the ball. When I throw it up, then at the top, when it comes to a stop, gravity doesn't disappear. So it now starts to speed it up downward, and when it returns to my hand, it comes back with all the kinetic energy that had before. So that's a more of a qualitative, intuitive description I'd like to give to this feature. And I'll give you the mathematical description. This conservative force, it has to be a predictable force. As in, it has to be a force that given really one parameter, you need to be able to predict what that force is going to be. So that if you take a path going from one place to the other, losing some kinetic energy, you have some confidence that as you take the other path backward, you can regain that lost kinetic energy. That's not something you can say with the friction force. That is something you can say with the gravitational force. And what about with the spring force? Is the spring force predictable? Yeah, it's not constant, right? But it is predictable in the sense that when I stretch it out here, at this position, spring force is always going to be upward at a particular magnitude. It doesn't matter if it was moving downward or moving upward. So when I drop it here, the kinetic energy lost moving downward, there's a confidence that we'll gain it back as it moves back up. So to make it predictable, really mathematically this is what it means. Mathematically what it means is that force is a function of position alone. So if the force depends on anything else, with the case of friction, the other thing it depends on is velocity. It depends on relative velocity. So friction doesn't depend on position alone. That's why friction is not a conservative force. Any applied force is not a conservative force because it depends on sort of my whim. If I decide to apply force on this ball, then I give it energy. If I decide not to, then I don't give it energy. So in physics 4a, those two predictable forces you've seen are gravity and spring force. So now this is the question we are posing. For the electric force, is it predictable the way gravity and spring force was? Is it function of position alone? Yeah, I mean, look at those formulas for electric field. I mean, for static electricity, yes. So yeah, they're all functional position alone. So they are predictable. Here, wherever the charge is, we can say the force will be always rightward, with this magnitude. So the starting point for us is that electric force is conservative. That means it's predictable. When you lose some kinetic energy due to work being done by electric force, you have confidence that you will get it back at some later point. So you can define a potential energy based on the work being done by electric force. So here, let's actually do that. We actually know the force for this simple situation. So I'm going to say potential energy is 0 here. So what I'm interested in right now is calculating the change in the potential energy as I move from this potential energy 0 to where hopefully I have non-zero potential energy. So along this path, what is the change in potential energy as I go from point A to B? As I go from point A to B. All right, I have this expression to fall back on, so let me use that. My magnitude of force is going to be, let me keep it a little bit general. So I will say my force, so this is going to be minus conservative force dot product with the displacement. So for the conservative force, let me put it as charge times the electric field. So it's minus of charge times the electric field. Dot product with the displacement, delta x going from A to B, delta x A to B. Now, when I do this dot product, am I going to get a positive number or a negative number? Negative. Force points to the right, displacement points to the left. So this whole thing will give me negative number, which will cancel out with this, which means the change in potential energy will be charge times the electric field times the distance that the charge moves. So this is the expression for the change in the potential energy, electric potential energy in this case. And if I want to find the velocity, then I can now set up this equation. Initial potential energy, QE delta x is equal to the final total energy, 1/2 mv squared, and I can solve for v. V is 2q e delta x over m square rooted, or something like that. Like simple conservation of energy calculation. So the concept that I want to introduce now is closely tied to this calculation that we are doing here. So for what we did just here, you didn't need me to introduce anything new. The only thing new that you had to know was that electric force is conservative. But if you have been reading the book, they do cover it. If you read the book, you would have seen this. So nothing that we did here in the last 20 minutes actually required us to know anything new. Now I want to introduce something new, motivated by the same reason that motivated me to come up with the idea, well, not me, other people, to come up with the idea of the electric field. So something about this expression here is a little bit unsatisfactory. This expression here, the change of electric potential energy as you go from point B to A is charge times electric field times the displacement. Or in this case, I guess the displacement is D. So charge times electric field times D. I don't like something about that particular expression. I would like to be able to sort of separate the expression out into two parts. Any guesses what two parts? Yeah, so charge, this charge that I placed, and really the rest of the setup. So when you look at this whole entire expression here, what you hopefully will notice after staring at it for an hour or so, or shorter, is that this second part depends, that's the property of the setup. When you have all these charges set up, then you have the electric field, and part of the setup was having this distance d between the plates. So everything on this half is part of the setup. The charge is something new that you have to place in. Maybe next time you place the charge, it'll be a bigger charge. Maybe it'll be something else. So right now here, the way this is written, it's always a paired thing. It's always charge paired with the setup. And we would like to separate it so that there is some property of the setup that we can calculate before we have any kind of charge. And when we have the charge, all we would have to do is we would have to multiply the charge to the new property that we are introducing and say that's going to be my energy. So this is the introduction to voltage. So this is how we can define voltage. You can describe voltage in two different ways. It's defined by only one of them, but let me describe voltage in these two different ways. Voltage, or this first time only, let me give it let me give you all the possible names you might see what I'll call voltage in this class from now on. The many names of voltage, it has electric potential is the actually standard name. I will explain why I won't use the name electric potential often. I prefer voltage over electric potential. It's potentially confusing. What other terms are there? I think there's only one more term that I really hate. I'll mention it once, and I will try not to bring it back again. There's a phrase called EMF that you will see referred to as voltage. What this EMF stands for, it's a very old-fashioned term. It stands for electromotive force. And it's just wrong in so many ways. It's not a force. It's a voltage that we are going to define, which is not a force. So this particular name is very problematic in many ways. Giancoli actually likes EMF a lot because Giancoli is an old textbook. In this class, I will use the term voltage almost exclusively, but I want you to know that these three words refer to the exact same thing. They are just synonyms for each other. So voltage, this is how we define it based on the discussion we had here. So the way we would define voltage, represented by symbol V. So looking at this expression here, I realize if I move this Q over to the other side here, then this quantity, that's the property of the setup that I want to set apart by itself, or what I would call this voltage V. It's going to be the energy, potential energy, divided by the test charge. So you could describe voltage that way. This is the connection between voltage and other mechanical properties that you might know about. So voltage would be electrical potential energy, electric, on some charge Q, some test charge Q, and you divide out Q. So this is one way of describing voltage. Now, although this is the intuitive one, this is the one we introduced first, this is not how voltage is defined. So for the actual definition of voltage, this is the thing that we can always rely on. Because here's the thing that's unsatisfactory about this way of describing voltage. It involves the test charge. And I thought we were trying to get away from the test charge. So why is test charge in the definition? So this is not the definition. The definition is actually based on this. Based on this quantity here. Electric field times the distance. But for that, I actually want to come all the way back here, back to here. Potential energy is the conservative force times the displacement, right? So let me write this out for assuming the conservative force is electric force. So this is going to be equal to minus Q times E dot D, or E dot, let me keep the same symbol, displacement, right? So let me do what's suggested by this expression here. Divide out both sides by Q. Divide out both sides by Q. Then Q's cancel. And what I end up with is minus E dot displacement. This is the quantity that we are going to define as voltage. So for the actual definition of voltage, this is how we define it. Voltage is defined. Let me indicate that with the 3 lines. It's defined as minus electric field times displacement. Yeah. Now, so when we are talking about the displacement, we are talking about going from some point A to B, right? So here, the voltage will be also some change in voltage going from point A to B. And for a simple setup like this, this works fine. That electric field, I have a value of electric field there times this. But we are going to want to talk about voltage in a more broader setting. We are going to want to talk about voltage of a point charge. So, point charge has electric fields that look like this. Anybody tell me, can someone tell me the formula for the electric field? Yeah, it's on the board. Q over 4 pi epsilon, not distance squared. And r hat 2 indicates a vector quantity. So if I'm talking about voltage change going from point A to B, my electric field strength is going to be changing. So this definition is the one that will work for constant electric field. I do like a version that's going to work for electric field that's dependent on position. How should I change this so that I have a definition that's valid under all situations, even ones like this one? How do you approach situations like that? It's the same approach we take in physics every single time this happens. Yeah. So once again, when you say take the integral, I want you to describe the steps, because we do not mean this. We do not mean doing that. That would be the wrong thing. Yeah, I never say the word take the integral. That's what the students say, and I correct them every single time.
Okay, recognize that the electric field is changing.
Okay.
Use calculus
Once again, you're not describing it. So yeah, that's not the description. So it comes down to, it's easy for you to memorize the formulas taught in calculus. Well, before integral, what did you learn in calculus? No, not derivative. How was integral introduced to you in calculus? Because that's a magic formula you're given. Not rate of change, that's a derivative. Yeah, there was a word for that. Do you remember it? Riemann sum. Yeah. Integral is the limit, the Riemann sum in the limit where the interval is infinitesimal. And so here's the thing. In this class, one thing that you are going to be doing a lot is you are going to have to set up the integrals. And if what you are memorizing now is that integrate, then you are not going to know the steps to do it. What's important in this class is, so what was important in calculus class was memorizing all the antiderivatives and memorizing all those rules. That's not important here. You see me use all from alpha whenever it gets any kind of difficult. So what's important in this class is your ability to be able to set up those integrals. And to be able to set it up, you have to know the proper procedure. And the proper procedure isn't that you integrate. That's not the procedure. Proper procedure is that you break this up into tiny little steps, as you do when you are doing Riemann sum. And you handle each tiny step at a time. So I want you, whenever a physics problem requires you to set up an integral, I want you to go back to that picture where we are setting up the Riemann sum. So here, we are, instead of saying it's electric field times the total displacement, what we are going to say is that it's going to be the electric field times, it's still a displacement, but it's a tiny amount of displacement. And when we are trying to say tiny, infinitesimal, this is the symbol that we use to represent it, right? So this is the thing that you are starting out with, but you don't end there. This is where you now finally integrate. This is the thing you are going to integrate, and now when you finally integrate it from A to B, then this is equal to this. So you've done this several times in physics classes by now. You've seen me do this in physics 4A when I derive the formula for the potential energy. You have done this when you calculate the rotational inertia of a body that's rigid body that's rotating. You have done this in thermodynamics when you calculate the work done by expanding gas. And what I'm telling you is that it's the same setup procedure that you are going through, but you have to understand what you are doing. Otherwise, when you see a new situation, you'll just get lost. So this is the definition of a voltage. One peculiar thing I want you to note is that we are not defining actual voltage, we are only defining the change of voltage. Right? It's a bit peculiar. We are only defining change of voltage, but that should remind you of potential energy. So with the potential energy, we only talked about potential energy from some reference point. And for the gravitational potential energy, you could change the reference point, and that wouldn't really change anything real. And it's that continues with the electric potential energy. Now, under some situations, we are going to have a preferred universal reference point. I will do that on Monday. In the remaining 4 minutes or so, let me show you some graphical tools that we use to help visualize the voltage. So you've seen this before, so there's a little bit of familiarity here. So you've seen the electric field. And one thing that this tool is able to do is it can demonstrate something called the equipotential. So it can draw, so you have experience drawing lines that represent electric field. So you've drawn electric field lines before. Now, what you can do with this tool is you can draw a set of lines that helps you visualize the voltage. Now, unfortunately, or maybe kind of like with electric field, if you simply go to voltage, that doesn't really do it. That's not the tool I'm talking about, because it's doing gradient thing. The tool that you need to use is actually this tool here. So this is the tool that's going to draw equipotential. So we'll derive the formula next Monday, but as you get closer to the positive charge, there's a higher voltage corresponding to higher potential energy you have. As you go farther away, lower potential energy. So with this tool, what I can do is I can mark out all the set of points that's at the same electric potential or voltage. So let me do that for a few points. I don't have a lot of time to do it, so let me just do maybe 5 or so. So I'll start out at 12 volts. So I'll draw one at 12 volts here. Looks like a circle. Does that make sense? That circle is the set of points at the same voltage. Yeah, let me do it for a few more. So 12, I'm going to go down to 8. Let me go down to 9. I'll do it in spacing of 3 volts. Let me go down to 6. Close enough. Down to 3. Do you see something interesting happening? Sorry? Krista, could you say louder? I didn't quite hear it. Value is decreasing. I don't know if I would call that interesting. That seems kind of obvious to me. Like, it's not very interesting that value is decreasing. I expected it. What else do you see that maybe you wouldn't expect as easily as value decreasing?
Not having a uniform rate.
Yeah, the spacing is increasing. So that's something interesting. And we'll talk more about this on Monday when we have proper amount of time to actually go through this without rushing through it. So, but let me leave this here and talk a little bit about equipotentials. So this relates to the graphical tools that we are introducing to talk about electric fields and voltages, because these are somewhat abstract quantities. That's why I keep highlighting this is how it relates to the force, so that case by case, whenever you feel like you're lost, to talk about electric fields, you can always connect it to the force, and that's why I start out with this here. So that if you feel like you're lost, hearing about voltages and whatnot, you have this as a reminder to you that it always relates to the potential energy due to electric forces. So this is there as a reminder, but that's more of a last resort tool than anything. When you are considering a new situation, it helps to have a graphical tool, and that's what field lines and equipotential that I will introduce are. So this is the simulation that I was using last time. And I'm finishing up your lab exercises you are going through today. And there's one part where I'm encouraging you to use this also. So hopefully after lab today, you'll feel more comfortable with all of this. So, imagine a charge is out there. So this is the vector field of the this is the electric field vector field representation. As I keep mentioning it, this is kind of hard to draw by hand. I'm never going to ask you to draw it by hand. But what I am going to do is use this picture to draw the electric field lines. Okay? Let me draw electric field lines with the 8 field lines for this single charge. You've seen it a few times, so you know what it looks like. I'm going to draw 8 lines going away from this positive charge. So that's 4, 8. So when you're drawing electric field lines, the key thing to remember is the direction of the electric field. So here, they are all radially outgoing from the electric field. So the point where it corresponds to the lattice, you can actually see the direction that you are going. Points where they don't correspond to a lattice, you have to use your imagination. Like over here, it's going that way. Over here, it's going that way. So in between, it's just moving straight up. And when you're drawing electric field lines, this is the idea. At this point, the field line is telling you the electric field points away that way. So you move in that direction, and you reevaluate. What's the direction of electric field now? Well, it keeps going up. So here, as you continue to reevaluate, you get this as the direction of electric field. And when you draw it as an unbroken line, that's when you get electric field line. It's exactly what it sounds like. And the procedure for drawing it is simple. You just draw the direction of the field line, only paying attention to the direction. So you should start out with the correct starting point, single charge, and it should be sort of spherically symmetric around it. So I started out with a uniform distribution of lines. But once I've done that, the rest should just fall in. Rest in the sense that these are what the lines would look like without introducing any complicated rules. Or once you have drawn it, these field lines obey a particular set of rules. The one that I remember mentioning last time we were talking about electric field lines was relating to the electric field magnitude. So in this figure, the electric field vectors, the magnitude is actually indicated through the opacity of the arrows. That's why if I say direction only, they all become equally opaque. So when they get dimmer is where they're supposed to have less electric field magnitude. And actually, I haven't used this yet, but you can illustrate with the sensors. So this is the electric field sensor. When I bring it closer, you can see that it gets larger. When I bring it farther, it gets smaller. So, so when I'm talking about electric field lines, I'm talking about this. What you see without the vector field. And this electric field line, somehow the electric field magnitude is represented in this figure as well. Do people remember how electric field magnitude was represented in an electric field line? There's a graphical feature you can look for and say, this tells me when electric field magnitude is small and when it's large. Yeah, how close they are, or the density of the lines. So here you can see that density of lines for this point charge, it's proportional to 1 over r squared. And that actually corresponds to here. You have seen it before. And without going too deep into it, I will say that this connection, it's not accidental. It ties also into how Gauss's law expresses how the electric field lines should look like. So now, using this same setup, let me illustrate equipotentials. So you guys saw this picture last time, but only for a couple minutes. Let me spend a few more minutes this time so that you have some chance to start to become familiar. So, so this tool is actually, It takes a little bit of work, but you can actually use this simulation to illustrate equipotential using this equipotential drawing tool. Just have to do it by hand. So let me do it in more closely spaced than last time. So what I'm going to do is, let me start out at 20, and I'll use a spacing of 2 volts. Yeah. All right, so I'll just do it quickly. So 18, 16, 14. And as I draw this, here are 2 questions I want you to think about. 1, what do you think these circles represent? That's the first question. 2, if you wanted to use equipotentials to figure out electric field strength, how would you do it? So it's going to take me a while to finish drawing it, but as I finish it, those are the 2 questions I want you to think about. What do these circles that's being apparently drawn represent? And if you wanted to get electric field strength from these lines, how would you get it? All right, and I know I cannot get to 0, so I won't try. And there are supposed to be more concentric circles inside here, but for now, I'm gonna say our limited scale does not allow you to see that. So this is sort of the unknown black sphere. All right, so those 2 questions I was asking. What do these concentric circles represent? What's the one property tying them together? Why circle? Why not ellipse or square or something else?
Well, aren't they all the points that have the same magnitude away from the center of the charge?
You keep saying wave. We are not going to get to wave.
I never said wave.
Magnitude of what?
The magnitude of the strength of the electric field away from the same center of the charge.
Mm-hmm.
So all the points along that.
I see what you're saying. Yeah, so here it's going to be hard to illustrate that, but I will say for now that that's not the answer. And after this, we are going to look at the example of this charge distribution, where you know the electric field lines for this, what that kind of looks like, right? And with this, you are going to see that when I draw equipotential lines, you will see that the electric field strength is not the same along the equipotential line. Yeah. I mean, what does the word equipotential sound like? It's not a trick question.
Same potential.
Same potential or same field? Same potential, right? Otherwise, we would say equifield line. So that's it. It's exactly what it sounds like. The set of points that are drawn are the set of points with the same value of electric potential or voltage. Let me illustrate that with this 6-volt equipotential line. So around where I drew it, it was 6 volts, right? Any other point that's on the line is at 6 volt. Now here's the interesting thing about potential or voltage. Is it a vector or scalar quantity? Look at the mathematical definition here. Yeah, it's a scalar because it's a result of what you get by dot product. So with the electric field magnitude, you have to say things like, these are the lines along which same magnitude. With the potential, I don't have to bother with the word magnitude. I can say these are the points with equal potential because they don't have direction. Magnitude is all there is. Yeah. So that's how they are drawn. I mean, that's really the definition of equipotential line or equipotential surface. You take set of all the points at the same voltage, and that's your equipotential. That's why I can say for this line, for this circle here, I can definitively say, well, this is my 6-volt line or 6-volt circle because all the points on the circle are at 6 volts. So the second question, it's a little bit hard to guess at it, but so let's say I don't have any of the electric field lines that I have drawn. So I don't have any of these electric field lines that I have drawn, that they are gone. Maybe I shouldn't have erased them quite yet. But and let's say I'm even getting rid of my electric field pictures. So all I'm looking at are drawings of equipotentials. And somebody asks you, where is the electric field strongest? And why? How would you answer that?
Well, I would say it's strongest because where it's densest. I would say it's the strongest where it's the densest.
Where it's densest, why? So that is the correct answer. So where it's densest, where it's denser, here, it is electric field is stronger. But why? It's the correct intuition, but
Because when we found electric field, we did it over an area, so it got weaker over.
so you're just remembering that with the discharge distribution, that's what electric field looks like. Later on, what I want you to look at is something that looks like this. This is what I want you to look at eventually. So you don't know what charge distribution is generating this, and I want you to answer, well, where is electric field the strongest? So I want you to answer something based on the features of equipotential alone and nothing else.
If it's denser, it's greater potential.
Now, let me have you think about it. So you are trying to associate greater electric potential with a greater electric field. Sometimes that's the case, not always. So whenever you feel like you are struggling with a concept, the thing you do in physics, this is how we do things in physics, is you fall back on definitions. That's why we spend so much time introducing these definitions. So the thing you should fall back on, whenever you feel like you're struggling with something, whenever you're struggling with the electric field, you should fall back to the definition. Whenever you feel like you're struggling with the relationship between electric field and potential, you should fall back on the definition. So based on this definition, how can you argue that where the equipotential lines are spaced closer together, that somehow the electric field should be stronger? It helps if you see the inverse relationship of this definition. So this is the inverse relationship of this definition. So you can actually turn this relationship around. It's actually easier to do it with this one, so I will do that. And then I'll do that for this one also. So, so let's say somebody asks you to solve for electric field here. It's a simple matter to just algebraically solve for E here, right? So let me do that. When I solve for electric field there, I'll just say I'm solving for electric field magnitude, not, so my electric field along the direction x is, move this over there, multiply by minus, so it's minus change in voltage as you go from A to B over change in distance as you go from A to B. Does this sound reasonable? Or you go back the other way. Assuming this is the electric field component along x, you take that product with this, you should get this back, right? So when you look at this relationship tells you where the spacing is closer, the electric field is stronger. The way I drew these equipotential lines, what can you say about the difference in the what can you say about the difference in the voltage from one line to the next? What was the difference in voltage, the way it was drawn? Same voltage distance, right? Here, in this case, it was 2 volts. And between one and the next one, it's the same voltage difference, 2 volts. And that's, by the way, one of the conventions we follow when we draw equipotential lines. We make sure that the spacing of voltage we use is the same spacing for different points. So the way this is drawn, the delta V is always a constant quantity. So what do you expect to see with the delta X as electric field gets stronger? You expect a smaller spacing. So that's what you see here. So it's stronger here because the spacing of delta X is getting smaller. So here it's not explicitly about density. With the field lines, it was density. Here it's with actually spacing between the two equipotentials. Okay, I think this is about time we should go to break. But before we go to break, let me just give you another example of equipotential so you have something to think about. Let's see, erase everything. Let me do this one. So, you have seen the dipole electric field, but you haven't seen dipole equipotential. So I think it's good for you to see what it looks like. So that looks like a dipole field, right? Yes? No, I won't draw the field lines since that'll take too long. So let me draw equipotential. This time I think I want to start out with a 0 volt. Do you think I'll be able to find the 0 volt anywhere? Last time, with a single charge I couldn't, so I gave up. Here, any guesses where I might be able to find the 0 volt? Yeah, between the two. Right in the midpoint between them is 0 volt. So let me try to get as close to it as possible. That's close enough. Yeah. So that 0 volt equipotential is the one starting from here, perpendicular to the electric field, going out to infinity. So let me draw them in 2 volt intervals. Well, again, I'll draw, maybe I'll draw, see how many I can draw and then stop at about right point. So this is the 2 volt equipotential, 4 volt equipotential, 6 volt equipotential. Maybe I'll stop at 10. 8. Yeah, let me stop at 10. I have to do the negative side. So it'll be -2, -4, -6, -8, -10. Does the shape you see kind of make sense? Like what you would have expected if you didn't actually expect it? But okay, does it make sense? Yeah. Let me ask you one interesting feature that, highlight one interesting feature that's already here that's useful to know. So let me take this point here, for example. This is the direction of electric field, right? Let me take one other point to use as an example. Here, this is the direction of electric field. Do you see any relationship between direction of electric field and direction of equipotential? What relationship do you see? Yeah, they're always perpendicular, right? Like once you have that idea, test it for any of the other points. You'll see that they are always perpendicular. So that's somehow a property of equipotential surface or equipotential and electric field, that they're always perpendicular. Can you justify that based on what you see in the definition here? And I'm kind of running out of time, so let me answer the question myself. So this is how you justify it based on this definition here. Essentially, I imagine potential difference between 2 points, relatively closely spaced here. So potential difference from, let's say, point A to point B, right? If I'm going in the direction that's perpendicular to the electric field, what's going to be my right-hand side here? 0, because the dot product will be 0, right? So if this displacement, delta x A to B, is perpendicular to the electric field, that will guarantee that your potential voltage won't change according to the definition here. And that's why you see this graphical feature. Because as you go from this point A to this point B, you are sort of guaranteeing that the path you are taking makes sure that your voltage won't change, because the dot product of electric field and displacement is 0. Okay? So I think that's all the graphical features I want to point out in the lecture today. In the lab, you will have some time to play with something like this and try to develop more familiarity. Welcome back. With the next example, voltage of a point charge, let me introduce 2 ideas. One is the formula that you will see used from time to time. And second is the idea of a universal reference point. So it comes down to this point here. When you look at the electric field lines and the voltage of a dipole charge distribution, you might wonder, so we say this is the voltage equals 0 line. So why is it voltage equal to 0 here? I mean, when we're saying how with the potential energy, so also with the voltage, it's really the difference that has physical meaning. So what lets us set like an absolute reference of voltage equal to 0? Like, is there anything special about voltage of equal to 0?
Just because it's perpendicular to the electric field line?
So perpendicular to electric field line, that says the change of voltage will be 0. Yeah. So, but I guess you can actually put it this way. So if you take a point here, there's something special about this point here that you can connect to it to another special point using only paths that are perpendicular to electric field. So this is what I would call, what I like to call universal reference point. Let me call this universal reference point. So I don't know if anyone else calls it that. So the idea I'm trying to introduce here is that most of the times reference point that you are using is local. As in, you define it for a particular problem. I define height to be 0 here. And then from then on, like for that problem, height is 0 here. But for a different problem, height might become 0 at the floor, right? So those are local reference points. But especially as we talk about electricity and more like universal laws of nature, it's convenient to have a universal reference point. You could call this the default reference point. It's the reference point that's useful not in just one problem, one situation, but it's a reference point that's going to be useful for many different problems and also many different observers. Like, with the two reference points I was talking about, someone who's standing here versus someone who's standing here, the two reference points, it makes sense for different reasons, right? This universal reference point that we are going to define and use, it'll be useful for everyone. In the context of gravity, it's a reference point that's going to be useful for me, useful for someone in Canada, someone in New York, someone in India, someone in China. Like everyone on the Earth. In fact, everyone in the solar system can use this reference point. Any ideas what reference point I'm talking about? Can someone describe this reference point? Like, for example, I want to know voltage produced by this charge here. And the definitions only give you voltage difference. And we are going to all agree to measure this voltage difference from a particular point that anybody who can see this charge has access to. So if you have a point charge, there are really two special points that you can talk about regarding the point charge. Somebody tell me one of those two special points. Point itself, right? So you might say, oh, so that's going to be my reference point. Then you look at the formula and you run into the problem. Because as d goes to 0, electric field goes to infinity. I don't want to deal with the infinities. So that's one special point that you might have wanted to use as a reference point. That's not going to work. There's a second point, actually.
So where electric field is equal to 0 then?
Where?
Electric field would equal 0.
Where is electric field equal to 0?
It's in like the midpoint between.
I'm talking about single charge. Yeah, I moved on to the example of single charge. But the way we are going to define this reference point, it will apply to single charge as well as to dipole charge distribution. So this is the second special point when you're dealing with a single charge. So Kevin, you said where electric field is equal to 0. Where is it equal to 0? So you're on the right step. So you are saying that you want this to be equal to 0. What distance d can you pick to make electric field equal to 0? we already handled the d equals 0. That gives me infinite electric field, not zero electric field. Yeah, infinity. When you are infinitely far away, at that point, electric field is 0. So that's the special universal reference point we are going to use. As in, so actually we do this in astronomy. The reference point we use is actually the stars. Stars in the sky, they are more or less infinitely far away. So sailors around the world have used the stars to navigate themselves. So what we are going to use is we are going to use infinity as our universal reference point. So that's that sense in which this is V equal to 0. We define at infinitely far away voltage equal to 0. And looking at this line, you can come to this point out from infinity. Only the paths that are perpendicular to electric field. So that's the universal reference point that we are going to use. Now, there will be some situations where you cannot use that universal reference point. Whenever you have infinite charge distribution, this reference point fails because you're dealing too many infinities. But whenever you are using finite charge distribution, either point charge or dipole or ring of charges, ring of charges, or a sphere of charge, you are going to be able to use this universal reference point. And whenever we are referring to this universal reference point, we are going to use this phrase that V of r goes to 0 as distance goes to infinity. So once again, realizing that you cannot use this for every problem, but for the vast majority of problems where you can use it, we are going to use this phrase to refer to that this is the reference point we are using. So using this universal reference point, let me derive a formula for voltage of a point charge. Got question? Comments? Okay. The first example I want to go over is a voltage formula of a point charge. So this is one of those formulas that's going to be useful to remember. So imagine I have a point charge here. And if it helps you, draw electric field lines so that you can sort of visualize what the effect of that point charge is. And you even know what the magnitude of that electric field is because you remember this. So the electric field due to that point charge as a function of distance r is 1 over 4 pi epsilon naught amount of charge over r squared. And I'm talking about the magnitude, so I don't have to worry about the r hat vector. Okay? So the question here, as you guess from the title, is what is the voltage as a function of distance? And if I want to be sure that I'm using this universal reference point, then I do say V of r goes to 0 as r goes to infinity. Yep. So let me do this one as an example. So all of these calculations, well, not all. This is one way of calculating voltage that's going to essentially apply the definition of voltage. So this is how we define the voltage, right? Yes? So we are going to start out by saying this, that voltage at point R, especially the way we define it here, it's going to be change in voltage. So let me call it a small, you add up all the small changes in voltage from R equal to infinity. So you start your integral from way out in infinity, and you pick a path to come closer to some particular point R, to R prime to R. So this is what I mean. So I imagine I picked a point at R equals infinity. And then this is the path I'm picking to come to this point at distance R. Good? Now, one thing that you should remember about this integral that we are going to do is this is something called a path-independent integral. As in, imagine I have a different point here. like this point here, then I'm not going to imagine me picking this path because that's going to be way too complicated. Instead, what I'm going to do is I'm going to follow this same path so that that part of the integral is the same. And when I pick this path along the equipotential, what is going to be my change in voltage? 0, right? And the claim that I'm going to make without proving it is that the two different ways of doing this calculation will give the same result. Do everyone believe that? Yeah, this is actually one of the properties of conservative force and all that stuff. So if you're interested in detail, read in the textbook. So I'm going to pick this radial path to help me do this calculation here. So now for this small contribution to the voltage change, I'm going to write out this expression here. Each contribution to voltage change is given by minus electric field times a small interval. Right? So this is equal to minus E as a function of R times dr. Integrated from my starting point. Sorry, I keep switching back and forth. Everyone here familiar with when people use primes when people are doing integrals? Yes? So I'm using R prime as the variable of integration. And the final R that I'm ending up with is the point where I'm interested in calculating the voltage. It's a common convention, but the primes are important that I don't forget them. Okay? All right, so this is my integral setup. As in, I imagine having this whole path, and to explicitly say it, what I'm imagining is I take up this whole path, divide into small intervals dr, and for each of these small intervals dr, the minus electric field times that gives me the small contribution to the change of the overall voltage. Add it all up, I get the total change in voltage. And because the way I defined, I'm starting at V equal to 0, I'm going to say that whole change is equal to the voltage instead of bothering with the whole delta V notation. Okay, so let's just plug in the formulas and see what we get. This is the formula for electric field. I know that already. So it's minus R prime from infinity to R, all of this, 1 over 4 pi epsilon naught, charge over R prime squared dr prime. I didn't mislabel any primes, right? Good. Okay, anybody here know how to do this integral? What's the antiderivative of 1 over x squared, I guess? It's good for you to remember that when you're trying to remember the antiderivatives, 1 over x squared is actually x raised to the power of minus 2. So what is the antiderivative? I heard 1/3, but that's not correct. No, 1/2 is also not correct. Yeah, negative 1 over x. Once you take guess the antiderivative, if you're not sure, take the derivative of the antiderivative. You should get the same thing back. If you don't, you guessed it wrong. So you have to keep guessing it until you get it right. Right? I mean, that's the only way you do the integral, and that's why integrals are hard. Because all the integral rules that you have learned are essentially guidelines on how to guess the antiderivative. All right, so let me do this. So I'm going to factor out everything that's constant, minus q over 4 pi epsilon naught. I'm trying to be careful with the sign this time because I'll explain it later. Antiderivative of this thing here, minus 1 over r prime, evaluated from infinity to r. So r prime goes from infinity to r. All right. 2 factors of negatives cancel out. That's one of the reasons I'm trying to be careful with all these minus signs, because there's ways to get the correct answer by making even number of sign errors. So let me continue. So I'm going to evaluate this at these 2 limits. I plug in the upper limit, 1 over r, minus, I plug in the lower limit, 1 over infinity, that's 0. So when I evaluate at the limit, the v at r becomes Q over 4 pi epsilon naught R. It's a surprisingly simple formula. And in fact, if you've been reading the textbook when we are doing physics 4a, you have seen this similar formula in the context of gravity. So gravitational potential energy due to Earth or the sun also goes like this, if you set the reference potential to be at infinity. Okay? But this is for electric potential. So that's it. So any questions? This is a pretty useful formula. Let me find a place to write it down. So I guess I'll write it down here. Potential due to a point charge at distance r is equal to Q over 4 pi epsilon naught r. It's a simple, nice scalar expression potential. So scalar in the sense that you don't have to worry about directions here. And I'm going to illustrate why that's a nice feature in the next example. Good? Everyone good on the derivation here? It's a pretty simple derivation. But the important point is that, so if we wanted to find the voltage from electric field, so you are trying to apply this definition here, then this is how you would do it. This is the sort of the simplest non-trivial example you can have. So, you might think, oh, we can do this the same way as before. And and actually you can. But let me illustrate a different way of doing voltage calculation that highlights how much voltage is easier to deal with, easier to handle than electric fields are. In the limited time we have in the class, actually let me do the ring charge, because that's something that we haven't done in class at all so far. So I think it'll be useful for you to see it. And that actually illustrates my point better. So let me, voltage of ring charge. Yeah, sorry about that. I should have thought this through. Okay, so this is actually a new setup. I think this example might be done in the textbook, but we didn't do this in class because we keep running out of time whenever I want to bring in something like this. And this is actually a good example of how sometimes dealing with the voltage directly is a useful way to handle a problem. So let me describe the setup. So, well, I guess it's easy for you to see this way. So this is what the setup looks like. Imagine you have a ring of charge. So let me draw a ring of charge like this. So here's the ring of charge. And let me say it's a ring charge of, let me make it easy for myself, charge density lambda. So if you wanted to relate it to the total charge, you could say that the total charge is lambda times 2 pi r, where r, capital R, is the radius of the ring charge. Good? Okay. And this is the question that someone could ask. And actually, at the level of this class, you could answer. It takes some work, but you could answer. So I define a special axis. Because if I'm asking for, so let me ask you this question. Does this situation look highly symmetric with a ring? It is somewhat symmetric. So let me ask you this question. Compare this ring case with this spherical case. Is this ring case as symmetric as the one with the sphere? No, right? There aren't as many symmetry operations you can apply here. Sphere, you can rotate it anyway, and it's a symmetry operation. With the ring, there's really only one axis where you can rotate it around, and it will be symmetric. Any other axis you rotate it about, it won't be symmetric anymore, right? So with this ring charge, it's not highly symmetric. It has some symmetry, and this is how you will see it. If you try to apply Gauss's law, you will quickly realize that there is no Gaussian surface you can define. Or at least the one you can define where you can pull out the electric field. That's why ring wasn't one of the 3 geometries that we went over. You cannot use Gauss's law. You have to, if you want to calculate electric field, you have to do it the old-fashioned, the difficult way. So this is the question that someone can still ask. And in fact, I think this is one of your homework questions. Define an axis that goes through the center of the ring and it's perpendicular to the plane and all that. And what someone could ask is, take a point at some distance, distance d. And someone could ask these two questions. What is the electric field at that point D? And what is the voltage at that point D? Good? Can everyone here imagine doing the electric field calculation? So I'm pretty sure I actually asked this in homework. So, in the homework, this is how you do it. If to find the electric field, you would consider contribution from different points. And this is one place where you use the idea of pairwise cancellation. You think about contribution from this part here, match it up with the contribution from this part here. Contribution from above, it will give you electric field that looks like this. Contribution below will give you electric field that looks like this. So you realize that electric field, so this is the net electric field from these two contributions. You imagine taking pair of points all the way around this. And you going through all of that, you realize only component of electric field that survives is along the x-axis. And then you integrate over the whole ring to get the total electric field. Good? If this doesn't sound utterly familiar, do the homework. This homework is already posted. You should be working through this homework. Good? I'm pretty sure this is one of the homework questions. So for the time today, what I want to look at is, what if someone asked for not the electric field, but the voltage? How would you answer that? And you could find the electric field and then do this integral and then do it that way. That's a valid way to do it. It'll give you the correct answer. But what I want to tell you now is that there is actually a shortcut. There's a quicker way to do this. Any idea the quicker way to do it? Do people remember superposition principle? I think the first time I mentioned it in this class, I told you it's going to come up often. That's why we give it such a grandiose name for something that's saying something so simple. What does superposition principle say? It applies with the forces, but I want it stated generally.
You just add them.
Yeah, so combine the effect of two different things producing something. It could be force, it could be electric field. Superposition principle says that you just add them together. You don't do anything complicated with it. And what I'm happy to tell you is that superposition principle applies to voltages also. As in, if you want contribution to voltage from this point here, and then contribution to voltage from this point here, all you have to do is simply add them up. Okay? Let me write it down in symbols. So this is what I'm trying to do. I'm trying to say that total voltage, so voltage at point D, it's going to be the contribution to voltage from multiple different points. It's going to be, so at this point here, the voltage here is produced by all these different charges. So it's going to be contribution of all these infinitesimal voltage contribution from those different points added up over the entire ring. Okay? I want you to be careful how what this symbol means right now is different from how I meant it when I derived this formula. So all this symbol is saying is that I'm adding up stuff. When I was driving this, what I was adding up was the change in voltage over small intervals, right? Here, what I'm adding up is not intervals. What I'm adding up are different portions of the charge that's generating it. Yeah? So I want you to keep that distinction in mind, because when I write down something like this, I haven't really said anything. This is my equivalent of saying, I'm going to integrate. Now, you have to explain how you are going to set it up. So here, remembering what this symbol represents right now, what I have to represent is what is the small contribution to the voltage at this point due to a small amount of charge, dq here. So that's what I'm going to write down. So this is dV, small amount of contribution to the voltage. Well, I look at this formula, think about it. Can I use it? I think I can use it, right? So I use it. So it's going to be the small amount of charge in this small section, dq, divided by 4 pi epsilon naught. Those are just constants. I'm just copying it down. The symbol I have to be careful with is this r. What does r represent in that symbol, in that formula? Distance, right? So here, if I just use r or d, that wouldn't work, right? What's the expression for distance from this point, or from this point to the point where I'm considering? What is formula for this? Yeah, use Pythagorean theorem, right? So this is d, this is r. So this is going to be square root of r squared plus d squared. Okay? So, all right, square root of r squared plus d squared. Is this going to give a complicated integral again? We'll see. So we are going to integrate this over the whole ring. All right. Okay, so I'm integrating this over the ring. Does anything on the right-hand side change as I do this, add up this quantity over the ring? Yeah, it shouldn't change. So if you are thinking that here the answer is that this whole thing is equal to the total amount of charge, lambda 2 pi r, divided by 4 pi epsilon naught square root of r squared plus d squared. If you're saying that this is the answer, yeah, that's actually the answer. But for those of you who might be skeptical, let me demonstrate it. Just going through the actual rigorous steps. So when you are integrating over the ring, this is what you have to do. You have to select a parameter that will allow you to go over the entire ring. Here, the natural parameter to do it is the angle theta, right? You can start out at theta equal to 0, go over whole angle of 2 pi, and that will give you the entire ring. So this is how I'm going to set up this integral. I have to first write out dq. What this dq in terms of theta will be is charge density, lambda, times I need a length that's expressed in terms of theta or d theta. And that length will be the radius r times d theta. Everyone okay with that? Yes? This is the small segment of this ring that's represented by d theta. All right, so that's what I'm going to write down here. The integral over the ring is theta going from 0 to 2 pi. dq is replaced by this, lambda times r d theta over 4 pi epsilon naught square root of r squared plus d squared. And to to quiet your mathematical conscience, you go through each one of these symbols. Do any of these change as theta changes? Lambda doesn't change, r doesn't change, none of these change. Which means this integral over d theta, it's equivalent to just multiplying by 2 pi. And when you do that, this is what you get. So this is my formula for voltage of the ring as a function of distance d. So I want you to know how much simpler this is. So when I'm doing this thing for the electric field, I guess it's not that much complicated, but I at least had to worry about the directions and all that stuff. When I'm doing it for the voltage, I don't even have to worry about directions, because this is a scalar quantity. As long as I'm convinced that superposition principle applies, I simply add them up. Okay. So that's it. And I'm not going to go through the actual calculation, but let me tell you that there is a way to calculate the electric field if you know the full expression for voltage. So, so I guess we don't use it as much as often as we should. It comes down to using this expression here. In calculus terms, this is what it is. The x component of electric field is minus the partial derivative of voltage with respect to x. Which means once you know the full expression for voltage, then you can use that to get back to electric field. So here you have the full expression for voltage. If I define my axis this way, this is x and this could be y, then the formula for voltage I have is v of x is equal to all of that, 2 pi lambda r over 4 pi epsilon naught square root of r squared plus x squared. Right? Then all I need to do to find the x component of electric field is this. I take this, take the minus, the derivative with respect to x. That's going to give me the x component of electric field. Yeah. So this operation, essentially, if you wanted to find the electric field, it turns one potentially complicated integral into a simpler integral plus a derivative. And you guys know derivative is always easier. Yeah. So that's just something that comes up more in the upper division electrodynamics class, but something good to know. So I still have to post your voltage homework. I might include 1 or 2 questions like this just so that you see how it's used. One caution though, could you use this to figure out the y component of electric field? Here you can't because you only really know voltage as a function of x. As in, if I moved slightly off the axis, I don't know what the voltage will be. So if you want the y component, then you have to expand this out. You have to actually derive the expression for voltage as a function of x and y. And that would take more work. That's why in lower division classes, we never ask you electric field and voltage off of the axis. And on the axis, you can make a symmetry argument that y component is 0. Yeah. Let me get started here. So it has some instructions. I'm going to go slightly opposite way. Here for questions 8 and 9, it's having you, it says sketch electric field lines and then do equipotential lines. And it says, if it helps, use the PHYS simulation to see what they should look like and copy it over. I'm going to do it the other way because I happen to be rather familiar with both the field lines and equipotential lines. I'm going to sketch it first, and then I will confirm it by going to the PHYS simulation that it does look like what I thought it should look like. So let me do question 9, where I say, let's make it interesting. So let me first draw the electric field lines. One thing I have to be careful as I do that is that I need to be sure that I draw 3 times as many lines here as I draw it here. I think I can manage drawing 9 lines here. So that means I'm going to draw 3 lines on this side, so that what I draw on the side over there looks reasonable. So I'm gonna try to draw 3 lines separated out that way. And let me, so I'm kind of planning these 2 pairs to connect to each other. And after that, nothing's gonna connect to anything because it'll just go out to infinity. I think that makes sense. So 1, 8, 9. Okay, that looks about right. Let me finish connecting these lines so that they connect. Oh, you know what? I think these 2 lines will connect to these 2 lines. That makes the most sense. So let me start by going radially outward, and then these are going to curve enough to come to here. That's kind of what that'll look like. And basically there's no line going out to infinity from the minus charge, which I'm fine with. And yeah, I can, none of these lines can come in because, and out here it's basically going to look similar to what a electric field lines from a point charge would look like. So I'm trying to draw it so that some of these lines, they do appear a little bit affected by the negative charge in that they're bending. This is bending the wrong way. So something like this. And, you know, at this point, this is very qualitative because I don't, I don't, it's hard to do this very precisely by hand. Now, here, there is still going to be a 0-volt line, but it won't quite be a straight line in the middle. For one, you can see that if I start out in the middle, there's no way it can go straight under the constraint that it's going to cross this at a perpendicular direction. So, so what I'm going to remember is this formula that you would see as you cover electric potential, which is that electric potential of a point charge is given by Coulomb constant times the amount of charge divided by R. So with these positive charges, I have positive potential that's going to infinite positive as I get closer to the charge. And this is producing electric potential that get infinitely negative as I go near it. So the point where, so the potential is the sum of the potential from each of these distributions. Electric potential obeys the superposition principle, the same way electric field does. So I need to find the midpoint where those two contributions will add up to 0. Because the contribution from the negative side is smaller at the same distance, the point where I have 0 volts, it should be closer, so that the contribution from this far away, larger amount of charges will be same in magnitude as the contribution from this closer negative charge. So let me mark this as my V equals 0 point, and I can see that if I, well, because I messed up with these lines, I think I could actually draw a straight line that will go through them and look perpendicular. But what it should look like is something that bends this, or something, actually, I think it should bend this way. Is that right? Yeah, because I think to have 0 potential still, it'll have to be closer to the negative charge. So let me try to find a place where I can cross reasonably. Maybe somewhere here. Looks roughly perpendicular, so I think it's gonna, yeah. This is where I'm eyeballing. So yeah, I guess maybe I didn't mess up as much with electric field lines as I thought. So the V equals 0 line will look something like this. And the rest, you know, without the guidance of the field lines, it's hard to draw them. But I think it's gonna end up closing a circle like this. We'll check with the PHYS simulation to see what that'll look like. And let me draw the rest of the equipotential lines. And the only thing I'm trying to make sure is that as I'm crossing these electric field lines, it looks roughly perpendicular. When you're drawing this by hand, that's really the only thing that you can check for. And you know, if I were somehow grading these, I gave this to you on an exam or something, then that's really what I would be checking for. In terms of things like spacing, unless what you did was really unreasonable, then you know, you are eyeballing. It's not going to be super precise. But in terms of crossing at a roughly 90-degree angle, that is something I can enforce. So this is what equipotential lines would look like. I only drew 3. There's more that I can draw, you know, near the negative charge, and you know, doing this by hand takes quite long. So let me not do that, but show with the PHYS simulations what that would look like. So with the PHYS simulation, I don't know what it'll do if I place 2 additional charges here. Okay, I got rid of the equipotential lines because they didn't apply anymore. So this is what electric field lines look like. It's or you have to imagine connecting some of these arrows. You can kind of see that electric fields around here look more radial, as in like they look like they just come from a point charge, and they bend more around here. To and so this looks similar enough to what I was drawing here. So let me find the v equals 0 a point. Oops, somewhere around here. Okay, so draw equipotential. Yeah, it looks like that, kind of circular with some distortion. What this means is at this point, the positive electric potential from the positive 3 charges here. Remember, there are 3 of them. Yeah, let me just move them a little bit so that you can see that there are 3 of them. A positive voltage contribution from these 3 positive charges is equal in magnitude to the negative voltage contribution from this one single minus charge, which is closer. Then you can work that out mathematically and all that. And let me just, what spacing do I want? Let me do it in spacings of 15. So here's 15 volts, 30 volts, and 45 volts. That, yeah, it again, it because the spacing is so large, it's missing some of the features. It's just looking like circles around the charge. But if I fill in these 2 gaps, let's say between in the 2-volt increment from 0 to 15 volts or something like that, I'll start at, or let me do 3-volt increments so that I need to do 5 of them. So 3 volts. Oh, I don't know if I expected that. I did know it would be very asymmetric. So 9, and finally the 12 volts. So that's what it looks like. No, yeah, I don't know if I expected that, but doesn't look all that surprising. So yeah, it's and the goal of this exercise was to get people familiar enough with the equipotential line, so that because when you have the charges, it's easy enough to calculate the potential and field. So those graphical tools, they're not as needed. Where they are more needed and helpful and really is useful is when you actually don't know the charge distribution. That's what this question 10 is showing. It's showing you some kind of arrangement where you can say this much, which is that um, these are what the voltages look like at 0 volt and 2 volt intervals up until 8 volt and minus 10 volt. But you are not explicitly given any charge distribution, and you are just asked what are the electric fields. And when you have that situation, that's when you need to know how to read the equipotential lines. And here, if you look at the question, drawing the figure and consistent with the shown potentials and possible distribution of charges. So looking at this, so let me draw the equipotential lines that would appear. So let me use the same color I've been using for electric field. So what you first have to know is that electric fields go from the positive potentials or the more positive potentials to more negative potentials. So let me start at some place so that I have a few that I can start following. So I can have electric field, let's say, crossing that way in a perpendicular direction. And I kind of continue connecting these. And this is almost like how I drew the equipotential lines. And then in that I'm connecting these lines while trying to make sure that whenever they cross equipotentials, this time fields crossing equipotentials, they cross in a perpendicular direction. And trying to enforce that will force you to curve your lines in certain ways, and it'll look something like this. So that's one. Let me just continue. Let me draw a few of them. I think drawing these all very detailed way takes a lot of time and care, but I'm trying basically not to be so obviously wrong. At least making sure whenever it's crossing at 90 degrees, and something like this. That's bad, but all I'm trying to do is make sure I'm crossing at 90-degree angle. Yeah, so that's obviously not 90 degrees, so I'm not keeping that. Uh, okay, let me draw a few more lines and then I'll be able to answer the question he was asking, what the charge distribution looks like and all that. Okay, so I think what you see here and in the left middle corner and what you see here are relatively easy. Here you see electric field lines going up, so you must have a positive charge here. Here you must have electric field lines coming in from the less negative portion to the more negative portion. So there must be some minor negative charge here. The difficulty is in this region here because one, you have two 6-volt lines. So I guess one thing that means is there can be no electric field going from here to here, because if you did that, then you would have situation where point here and point here shouldn't be at the same potential. And I know they're at the same potential. So what the line must look like is maybe something like, okay, I painted myself in a little bit of a corner. So let me just draw a sample of a line. Here I'm violating some of the rules, which is that these lines, yeah, the electric field density should be proportional to the electric field magnitude. For the moment, I'm not really observing that. I'm just trying to see what these line crossings would look like. And when you trace them out, this is what they end up looking like. That perpendicular here. So both of so it's so as you look at it, I hope you realize you must have a positive charge here, possibly a smaller positive charge than this, because around here you have 8 volts, around here you have 6 volts. So it makes me think it's a smaller positive charge. But there must be a positive charge here so that you can have electric field going from 6 volt to 4 volt, 2 volts, and so on. So yeah, I didn't quite complete everything here, but if I completed it, you would look something that looks maybe like this, and this needs to end on the negative charge, and to be able to do exercise like this well, you do need a good understanding of electric potentials, equipotential lines, and electric field lines, and and so it's huge. So a lot of students like to just memorize formulas or whatever, and for people who study that way, it's graphical questions like these that'll get you, because there's no formula you could have memorized that would have helped you with this. The only thing that will and can and does help you is actually understanding equipotentials.